TTL Computer 2. Today we'll be taking a look at our backplane and our hex display for our backplane. And we'll also just take a couple minutes just to review some quick changes on our reset circuit. Okay, so we're looking at our digital simulation, and if you remember, everything below this line is not going to be in our physical implementation. So everything above this line are pretty much what's on the screen here represents the elements from our digital simulation, which will be in our backplane. So you can see that I took our hex display from down here and we moved that up into our backplane design. We'll look at the details of that in a minute, but this is also our reset circuit. And I just made a few changes here following the last update that I posted to the community pages. So what I'm just looking at how we're using the NOT gates here. We have extra NOT gates, extra inverters that we're not using. So I thought we would use them to instead of leaving them inactive here. So we're not looking at the RC elements in the reset circuit. This button here and this line represents the reset signal coming in from our RC RC circuit that's doing the 2-second delay. But so this represents that signal coming from the capacitor, going through the first inverter that basically changes the analog to a digital signal. So, this is the output to that first inverter. So what we're doing here is we're taking that signal and we're splitting that. We're splitting it three ways. One piece of that signal is going to come up here and go through a couple of inverters just as a display. These are just going to be used as display drivers to have our LED indicator light for when the reset button is pressed. That will be there. But the other part of the signal, we're splitting off here and we're going through two additional inverters in parallel, one here and one here. And the input signals coming in parallel, and we're also taking the output signals from the two gates, joining them together in parallel. And that's forming our not clear signal. So what that's doing is we're just using those two inverters in parallel, and it's doubling the power that this signal can provide. So we're doubling the source and the sink current that this signal can provide, just so we have a good strong clear signal coming out of this chip, into our backplane. Okay, so that was just how we're fully utilizing that inverter as part of the reset circuit. Okay, and let's take a look now at our hex display. So on the surface, it looks like I just dragged it from the bottom and dragged it up here. That's not the case. So let's explode this and take a look at what we do have. All right, so this is the design. Before we were using a series of AND gates to do to AND in the signals determined to do the address decode rather for the address coming in to decode the 2010 address. So we were using a series of AND gates and inverters and to do all that decoding, and also to reason about the U clock and the write signals to generate the latching of the data value into the hex display. But I've changed over here just to using a single comparator, and this is the same comparator that we're using in the ALU, right? 74682. So you can see that we have the addresses coming in from the address line, a 15, 14, 13, 12, and 4 and 5, right? So these bits we're using to decode the address. And so those are the input signals, and then the comparison signals are here, right? 0, 0, 1, 0. 0, 0, 1, right? So that's the decoding that's the values that we need for those bits. And then we're also just using we're also piping into the comparator the right signal and the U clock. So this one chip now is doing all that logic for us. And if the address matches and the right signal is high and the U clock signal is high, the P equals Q is true, and this is an active low signal. So this is just what we need to drive our cool retro displays, and that's what we have here. Those cool retro displays I found are TIL 311s, and that's what we're looking at here, and that's what they require is a active low right signal. So you can see that we have each of these handles 4 bits of the hex display. This one is the high 4 bits, bits 4, 5, 6, and 7. And this display, the lower 4 bits, 0, 1, 2, and 3, are going to be displayed. Now, these till chips didn't exist in digital, so I had to make those. And we can take a look at that. And then, so this is just my my design to replicate the behavior of those cool retro displays. The display, besides doing the decoding of the binary signal to the hex display, it also provides a latch to latch in that signal from the from the data bits coming in. So I'm just using a 574 here is the chip that we use for our registers. And you can see that we have the 4 bits coming in, and then we have the right signal is just our clock signal to latch that in. So this replicates what we need, how we're going to be using the TIL 311s. And then this is really not part of the TIL display. I'm just using this for our simulation. Is we need to take the 4-bit binary output. We need to bring that out to the LED displays, the hex displays rather, in digital. So we can see that in a minute. But this is the mock-up or the design of the TIL displays that we're going to use. Again, there's 2 of those. And you can see here's that output here from the TILs, which is just for our simulation. That's why we have the X's here. We're not really that doesn't exist in our physical build. Okay. And then you can see here, this is where we use the two 4-bit outputs. We have the high 4 bits, and then we have the low 4 bits, and those come right into the hex displays that digital provides. So it's almost matches what we're going to do with our hex displays. Not quite, but as close as we can get in our digital simulation. And again, we want to do as much as we can, pin for pin on our chips in the digital simulation as we can get to what we're going to realize in our physical solution. Again, to minimize any chance of errors. Okay, so I think our last step here is to fire this thing up and see that it runs, both with the updated reset circuit and with our replicated TIL 311 hex displays. And we can kick that off. Don't need that. So we see that this starts up in a reset condition, just like our physical design will, right? So we've just powered it on. Our RC circuit here starts at low, and we're in the reset condition. And then the 2 seconds goes by, and then this can run. And we see our reset LED goes off. Our not clear signal goes high. Our computer is running, and we can see that our cool hex digit TIL 311 display is working. Okay, so I think this addressed all of the pretty much all of the active elements that I needed to um, design and prove out for our backplane design. Uh, my backplane design is already underway, and I'm at the point where I really need to drop these active elements into the design to start getting the geometry and the layout of the components as they need to be. But uh, I think that will be our next video. We'll start to look at how our digital simulation is looking in our printed circuit board design for our backplane. But we may do that in more than one video. We usually do one video per PC board, but we may break that down into two videos in this case. So that's it for today. Thanks for watching.